Welcome back to differential equations. In this video, we're going to be talking about direction fields. To make an analogy, when you first learned to study in algebra the graph of a function, you found that there were some tools that you could use to get the characteristics of the graph without having to actually do detailed analysis and calculations. When you got into calculus, you learned how you could use the extreme values in order to make that graph a little bit more clear, a little bit more detailed, and still avoiding having to look point by point at how the calculation works. And you also learned, once you had the picture of the graph, how to make predictions about the characteristics of the function, again, without having to look at the details of the algebra. Direction fields are an attempt to do the same thing to a certain set of differential equations. Not every differential equation is written in a way that finding the direction field is convenient or even possible, but when it is, it can really give you a good overview of what the solutions will look like without having to take any steps into doing algebra or calculus. So let me get my head out of the way and let's consider a differential equation where we're going to be thinking about things spatially this time. So we have y as a function of x, the thing you're more used to, not the function of t that we use most of the time in differential equations. So I want differential equations which we can write as y prime of x is equal to some function of x and y. Any arbitrary function will work here. The key thing is that you can get the derivative y prime by itself on one side of the equation, and the other side of the equation has x's and has y's and has some work that we can hopefully get done. Whenever you can separate y prime from everything else like this, you can easily analyze the direction field. Because when we think about the derivative, one of the one of the early applications we saw for the derivative was writing the equation of a tangent line. Y prime is the slope of the tangent line. And when the equation is given in this form, if we pick any x and y, we get the slope of the tangent line at that point. All right, let's look at a specific example to see why this is useful. All right, here is a very simple differential equation. Y prime of x equals x times y divided by 5. And when I say that this is a very simple differential equation, I mean in the not too distant future, we're going to see a tool for solving this differential equation explicitly, where we certainly wouldn't need to go through this kind of a hassle. But that simplicity is also what makes it a great first candidate. So what I want to do is draw some coordinate axes, and I'm going to draw these larger than you would expect you want to. So let's draw it even larger still. There we go. All right, so we have plenty of space to work with. And what I'm going to do is simply pick points and plug them into this differential equation. So let's start right here at the point 1, 1. If I plug in x equals 1 and y equals 1, I get 1/5. And at that point, I'm going to draw a relatively small line with a slope of about 1/5. Then if I look at this point, x equals 1, y equals 2, I'll have a slope of 2/5, which looks a little bit more like that. This line has a slope of 2/5. Over here, I would have a slope of 4/5. This is going to be 3/5. And up here would be 6/5. So I can draw in the slope at each of these points. On the x-axis and on the y-axis, I have slopes of 0. Um, those are pretty easy to draw in. And then I am also going to look in the other quadrants where we're going to start seeing some negative slopes happening. All right, something kind of like that. Now here's where things get fun. Once you have a direction field, you can start using it. Consider an initial condition. An initial condition is going to give you an x and y coordinate where your curve wants to start. If you follow the path that these little bits of line give you, it's going to try to direct your curve in a certain direction. And just by using that, we can make some predictions as to what the solutions of this differential equation are going to look like. A little bit of arithmetic, a little bit of knowledge of slopes, no algebra, and hardly any calculation required. That's why direction fields are so powerful. That's why they are so valuable. Of course, taking the time to actually draw this direction field was kind of tedious. That's not always what we're going for. Luckily, computer software can come to our rescue on that end. All right, here I am looking at a website for a direction field plotting program. I'll have the link for this website in the description. It can be a little bit annoying trying to type in the differential equation that you're trying to solve. One thing that I want to stress is that you do need explicit multiplication dots. So the other thing is that notice that the definition is already given to us as dy dt. I like writing these out dy dx when I'm doing them by hand because the xy plane makes a lot more sense to me. But we had our independent variable, which was t, times our dependent variable, which is y, divided by 5 was the one we were looking at. And we can set our display window up. Almost always the defaults are good enough. And then go ahead and click the graph direction field button right here. If I scroll down a little bit, I can get this graph, or at least most of this graph, on the display. I know a little bit of it's cut off at the top and bottom, but you get the basic idea. And you see some shapes that look very similar to what we had. The interesting thing about this software is that that's not the end of it. Not only will this software automatically draw in the arrows for the direction field for you, it will also, if you click at a point, it will use that point as your initial condition and it will draw out the curve. If I click another point up here and maybe a couple of points down here at the bottom, you can see that we get curves very similar to the ones that we figured out when we were trying to draw this by hand. But it's a lot faster. I can just click here at random and I can get a large number of curves to show up, giving me the characteristic that will occur in all of these different initial conditions. All right, so that's the value of this software. If I scroll back up to where I can enter in, when I first loaded this page, I had things that were something like sine of t times cosine of y, or maybe it was in the other order. But let's go ahead and take a look at this one as well as something that's quite a bit more complicated. Graph that direction field and then scroll down so that we can fit some or most of the direction field on the screen. And we see these arrows that are kind of doing all sorts of things. You've got some that are going up, some that are going down. It's a repeating pattern. And I guess we shouldn't be too surprised at a repeating pattern when our differential equation involves some trig. But I'm just clicking along down the y-axis in a couple of places to get some hopefully representative curves. Click some more wherever there's space that looks like it could be filled in a bit more. And we get these curves that are going through this repeating pattern over and over again. When it comes to interpreting these patterns, you have a number of options because there are so many different ways that differential equations can be used. But on our graph here, with the way this was set up, we have our horizontal axis is the time axis, and the vertical axis is the y-axis. So what we're looking at is a position or a displacement and how it changes at time. So simple example of this might be a mass hanging on a spring. Mass hanging on a spring. As time progresses, the bottom of the spring is going to go up and down. And so we're looking at that motion over time. If I started here, I'm going to go down, and then I'm going to eventually make my way back up. If I started here, I'm going to start by going upward and then eventually make my way back down. And if I started somewhere around here, I'm going to stay pretty well level the entire time. So those are the behaviors that we can classify without having to do any calculations. That's where the direction fields can be so valuable. All right. All right. Let's jump back over to my notepad here and talk about two specific features that you can find in a direction field. When you're using a computer software to work through graphing the direction field, these become a little bit less useful. But there's still a lot of characteristic that you can figure out by looking at what are called the isoclines. An isocline is a curve on which y prime of x is constant. So going back to my first example, y prime equals x times y over 5. If I set that equal to some constant c, well, I can rearrange this equation and I can write that y is equal to 5c over x. That's something that I understand. I know what the graph of y equals 1 over x looks like. It's the curve that looks kind of like that. Let's get that a little bit more clear. And I know what the curve y equals 2 over x looks like. It's the same curve, but kind of balloons out in the middle a bit. So there's some space between here and things get really narrow up there. And I know that y equals 3 over x is going to behave much the same. I know that y equals negative 1 over x is going to do the same thing, but be on these quadrants instead. And I can fill those out really quickly. Once I have those, right, on every single one of these, figure out what the value of c is and draw your slope equal to c. It's a nice, quick way of talking about what the direction field is going to look like without having to work through and calculate by hand each of those steps. Again, figuring out a slope field by hand is not pleasant. It's not something that I think that everyone should do it once, and once is enough. So thinking about isoclines in the days of modern computers is not really all that useful, but it's still vocabulary that you might run into, so I wanted to at least mention it. There is a specific isocline that is valuable and is used in a couple of other places, and that is the nullcline. The nullcline is the isocline where c is equal to 0. Or in other words, the nullcline asks you to identify a curve on which y prime is equal to 0. And that's something that should be ringing some bells to you. thinking back to calculus, what did we know about a function when we could find the places where y prime was equal to 0? How did we use that? Hopefully, your mind is coming to this idea of critical values. Those are places where the function reached its maximum or its minimum. And so that is still something that can be very valuable to us in this process of looking at direction fields. All right. So we'll have some problems that we look at later on exploring isoclines and specifically noclines in a little bit more detail. But for right now, I just want you to get practice using this direction field plotting tool. So let me get my head out of the way and let's try to write something interesting down. All right, so here is a differential equation for you. Y prime of x is equal to 2 times e to the x all over y squared. I would like you to plot the direction field using software. I don't want you to try to plot this one by hand. I want you to use that software to draw a few representative curves. And for this particular equation, when you're drawing those representative curves, you should see something a little bit strange happen that didn't happen with either of the two direction fields that I drew in this video. I want you to try to explain in just a few words. Sorry about that. Everything is falling apart. I want you to try to explain in just a few words what happened and see if you can figure out why. If you can identify where the strange behavior is happening, and it will be very obvious what the strange behavior is happening. If you can identify where it is happening, that should give you a big clue as to why it is happening. But in any event, I want you to play around with that for a little bit, see what you come up with, and I'll see you in the next video.